First, I want to thank the organizers for inviting me here. And then, since a few things were said before, I will just go quickly over them. We have A is a C-star algebra. I will call U the unitary group. And B in A will be a C-star sub-algebra. And UB will be the unitary group of B. And what I want to study are the homogeneous spaces of the form P equal U over UB, in the sense that I will not make very explicit here that U operates on a Banach manifold P. The isotropy of this operation operates in a C infinity way, and the isotropy algebra group of this operation is UB, the unitary group of a subalgebra. This is the homogeneous space that I want to study, and the type of homogeneous spaces I want to study. Examples. We call in our paper this is joint work with some of these, and also Carlos Duran. And so we study here these homogeneous spaces, and the main examples we want to use here are, first, the Grassmann manifold of the C-star algebra A, meaning this, you can have different representations of this space depending on which one you like best. For example, a set of rho, where rho are reflections, orthogonal reflections, rho squared equals 1, and rho star equals rho. And this is P. And the group of the algebra operates by inner conjugation. And once you fix a reflection rho 0 in the algebra, you can symbolically represent the elements of the algebra as 2 by 2 matrices. And in that representation, you have the isotropy, well, the general unitary group is given by any element of the algebra can be represented in this way. And the unitary group of the algebra is like this. And the isotropy of rho 0 in this representation is, of course, given by unitary matrices of this form. And this is the homogeneous space corresponding to this situation. This general situation can be generalized to flag manifolds, finite flag manifolds if you want, by considering systems of projections P in the algebra A such that these are projections, self-adjoint, and they are mutually orthogonal, and they add up to 1. Again here, the unitary group this is a subset of the algebra, and it carries a Banach manifold structure natural because it's in the algebra. And this is a subset of the product of the algebra several number of times, and it carries a natural Banach manifold structure. The unitary group operates here by also inner conjugation, and the isotropy is like this, but now you have n blocks instead of 2 blocks. And so this is another example. This is as a reductive example, and this is also a reductive example, but in this case, this is very particular among all the homogeneous spaces I'm going to look into in this talk. And, these are made for other people, not for me. And you can even generalize the second example to what one could call spectral measures. With values in a C-star algebra A, in which case, instead of having P1, Pn may be thought of as a measure with values, projection operators in A, defined on the finite subsets of 1n, and you can generalize that by thinking of spectral measures, and you just extend the natural notions of the action of the unitary group, and you get the isotropy. The interesting thing, for example, about this third example is that in the first 2 examples, it's easy to define a reductive structure in the Lie algebra of the unitary group referring to the isotropy. It's easy to define them explicitly. When you consider a general spectral measure, there exist reductive structures, but they require some doing in the construction, and we have done it some time ago in a paper. So it admits the isotropy algebra admits an invariant supplement, closed invariant supplement. So these are the examples I will present, and these and the general context is this. And now I will come to the metric structure. So now I'm thinking in general, U over UB, and this I call P. And the metric, the Finsler metric on the homogeneous space is like this. So I usually do this picture. So this is P, this is U, and this is UB, and this is 1, and this is rho 0. And here is the Lie algebra of U. And so the Lie algebra of U is the subspace of self-adjoint elements, anti-self-adjoint elements of the algebra A. And if every tangent vector here, Z, defines by projection a tangent vector X at rho 0. And you can study the norm. Some people have told me that it is ridiculous to insist in this metric structure but I claim that it is the only metric structure that you have in the general context of C-star algebras. So it's not a whim of my imagination to consider this, but it's inevitable, and so I will do it. Yeah, I'm sorry. So you can consider the different approximations to the norm of x by considering different lifts of x to z and the norm of z. And the norm of z has the only possible meaning for the norm in a C-star algebra. It's the norm of the operator that z is. And then you define, you know what the norm of z, and you define the norm of x. And of course, x is the class, is defined by the class of z plus any, I would call y, the vertical tangent elements to this vibration. And the norm of x is the nth, it's a quotient norm of the norm of z plus y, or y. I will call B ant to the anti-self-adjoint elements of the algebra B. So this is a norm, and this is a Banach space norm on the quotient space, and it's of course invariant under the action of the unitary group. So it defines an invariant norm on the manifold P, and we want to study the geometry of this ridiculous Finsler space, which includes those examples. And oh God. So the first question here is the question about geodesics, minimal curves. I have to point out that, as Esteban said before, this is a very it's not a good norm. It's not a good norm in the space. You see, this is a norm. First, the norm of the operator norm in the space of self-adjoint elements in the algebra is gotten by taking the maximum supremum of the elements in the spectrum of the self-adjoint operator, and it's a supreme norm. So the unit ball there, or the unit sphere there, is awful. I mean, it contains flat parts, and it has angles, all sorts of disagreeable things. But that's the norm I have, and therefore this is the metric I want to study. So, and the first question, of course, is the question of geodesics, that I would rather call minimal curves. And I can present one or two theorems relating to the answer to the question of how to find minimal curves. And if that is not enough, I am sorry, but I don't only have those results. But I think they are nice. I like them. So consider again the situation I said before, where this is a unitary group, this is the homogeneous space. This is a point in the homogeneous space. This is the isotropy, which belongs to, which is a unitary group of a sub-algebra B. And then suppose that Z in the Lie algebra of the unitary group, that Z is minimal. And that means that I call minimal a vector of the Lie algebra of U when the norm of Z is the norm of X, where X is the projected vector of Z. So the norm of Z is the infimum of the, so that's the reason why I call it minimal. And then, well, I should say, of course, I defined a Finsler structure on P, and therefore we have lengths of curves. So the theorem says that the curve, and then you take L e to the tz. This is the action of the unitary group. L is the left action of the unitary group on the homogeneous space, and Z is tangent to the Lie algebra of U. So e to the tz is a one-parameter group of unitary operators in the algebra, and this on rho 0 is minimal, a geodesic if you want, for, so I would call minimal a curve when it has the least possible length joining its two endpoints. The curve is minimal for 0 less than or equal to t less than or equal to pi over 2 norm Z. That means that it's minimal for all. It gives the distance from rho 0 to rho for every row of the form e to, like of this form, up to this value of t. Now, that's one of the reasons, the main reason, why Esteban spoke about these minimal vectors and how to find them and what can you say about them. They give I don't know if there are any other minimal curves that are not of this form in the homogeneous space. Maybe there are. These are the ones that I know how to find. And I know they are minimal. And there's a lot to be said about this, but you can see that if the sub-algebra is a von Neumann algebra, then over each x, you have a minimal lift. That's what Esteban told you. And since you have a minimal lift, you can say, using this, that for every tangent vector to P at rho 0, you have a minimal curve starting at that point with that initial velocity. That's clear, right? That's what so if you have so in a certain sense, in this horrible Finsler space, you have at every if the subalgebra is a von Neumann algebra, you have a sort of an exponential in the sense it's not anything like an exponential, but you at least have one minimal curve going up to this point in every direction. And possibly you have infinitely many with the same initial velocity going to different points, because I must tell you, this is sad news, that over certain tangent vectors to P, there are infinitely many, of course, minimal lifts. And it's not true that all the minimal lifts over the same vector in the quotient will give you the same curve. Never, almost never, will give you the same curve. So it's rather pathological, the effect that you have a minimal curve starting at the point with a given initial velocity, but you may have infinitely many such curves, starting with the same tangent at the point rho 0. That phenomenon can happen, and I will tell you other phenomena that will also terrifying phenomena that will happen. So in such a natural setting, because I claim that this is a natural setting for a norm in P given a general C-star algebra A. Okay, now no, that's a big question. That's a yeah. Well, I was keeping that thing for the no. I don't know a general theorem that will. Excuse me, I do. The vectors? Yeah, because you get them by action of the group. And the group preserves its metric. Yeah, sure. Yeah, they have constant speed, so to say, these curves. And much more than that. The tangent vector is, so to speak, parallel in, I don't know. They are given by the action of an element in the group. But the problem is that over an X, you may have infinitely many Z's with the same norm. And then they are minimal, and then they give geodesics. Okay, so now, to give you just a resumed idea of the proof of this theorem, a key point in the proof is the characterization that I think is very interesting of minimal Z's that Esteban commented on. Recall that. So I will put myself in this context that. So I have. I will call the Lie group of the unitary group, the antisymmetric elements of the algebra A, and the antisymmetric elements of the subalgebra B, and Z is minimal if and only if two things, well, there exists a representation of the algebra A in a Hilbert space H. I should tell you that in all my talk, the C-star algebras have identity, because well, in operator theory, many times you study algebras without an identity, and I will not. So Z is minimal if and only if there exists a representation of A in H such that, and a unit vector, that this is, in the language of C-star algebras, it's called a state. And this representation is given by a state of the algebra, but I will not talk about that. There is a representation of A in H and a unit vector Xi in H such that oh my. First, Xi is a norming vector for the square of Z. The square of Z is negative because Z is antisymmetric. So Z squared, I will use the same element in the algebra as the corresponding operator under the representation. Okay? I will not write a letter for the representation. I will think that Z operates in H. So Z squared Xi is minus lambda squared Xi, where lambda is the norm of Z, and 2, Z Xi is perpendicular to Y Xi for all Y in B. Now, this is a characterization of minimality, and I think it's a nice, a very useful characterization. It's the only one I know. Minimality in the sense of the quotient norm. It's easy to prove that if these two conditions hold, then Z is minimal, and for the these are vectors in H. I'm sorry. I'm using the same letter for the element in the algebra and the operator. Yes. Okay. But the other way, I mean, that if Z is minimal, you can find such a representation is more interesting. And that's a theorem. Now, having this, I will try to explain to you the strategy of the proof. And the strategy of the proof is like this. You see, this is a variational theorem that cannot use any form of calculus of variations because you don't have any form of differentiability here. So you cannot take derivatives of anything. So it requires ad hoc methods for this. And this ad hoc method is rather stupid, but it's the only one I know. One way of knowing that a curve has minimal length is the following way. You find a map from the space where the curve lives into some other space, and you're so lucky that your function has the following properties. It reduces lengths of curves. It preserves the length of the curve you are interested in. And in the test space, in the space where you land by this function, you know that the curve image of your curve is minimal. Understand that? That's a method. I call that a method, right? So you have a curve in this space that you want to show that it's minimal. So you find a map from that space into another space such that this map reduces lengths. Every curve goes into a shorter one, but your curve goes into one that has the same length. And on the other hand, in this other test space, you know that the image curve has minimal length. That's the only way I know how to prove this. And now the strategy of proof is to follow this plan. This characterization, in fact, this procedure I explained now goes in two stages. So you first find a map from the homogeneous, yes. Excuse me? I don't hear. If you have 1 and 2, it's easy to show that if you have 1 and 2. Yeah. But if you know that Z is minimal, then you have to construct this, and that's more difficult, of course. You have to construct such a representation. So the strategy of the proof is I construct first a map from P to the Grassmann manifold of the Hilbert space H, and then a map from the Grassmann manifold of the space H. I mean, the Grassmann manifold of the space H is defined by like these reflections, it's decompositions of H in two subspaces of a certain kind that you get. And then you go to the unit sphere. Well, it has to be the 1/2 sphere, the radius 1/2 sphere of the Hilbert space itself. So this is in the Grassmann manifold of the space, and then this is the unit sphere of the space. And these two maps are length-reducing maps. And both maps send that curve into a curve that has the same length. Now this is a unit sphere of a Hilbert space, and so it's a Riemannian manifold and infinite-dimensional Riemannian manifold, but an honest Riemannian manifold, and of course you know that geodesics there are minimal in length, and this reduces length, and the whole strategy. So, and the main step is to invent this map into the Grassmann manifold. And I will just say that, that the basis, I will not explain that, but I will say that the basis for the construction of the map into, because this map is just operating by a reflection, an element of the Grassmann manifold thought of as a reflection will operate on a fixed vector of H, and that will move the vector, and this is this map. But this map comes from this characterization of Z. And the decomposition of H that you will find, you find one element of the Grassmann manifold, and then the action of the group, which is compatible with the both situations, will give you the whole map. So you have to find it in one point. The point is rho 0, and the map you get like this. You take all yc with y in the sub-algebra B, and that gets you a subspace, and you close that subspace, and you take the orthogonal. And that is an element of the Grassmann manifold of H at the point rho 0, and then you extend that one point to one point map by action of groups, and you get this map. And you prove that this map is length reducing and preserves the length of the basic curve. And for this one, it's easy to do the same thing, and therefore the curve is minimal. And that's a proof. So it's simple, you see. No. But I explained it's one component. And no. And the map goes, it's like this. You construct one particular decomposition associated with this Z. And that decomposition you think as the image of rho 0. And then you extend that to the whole P. And that takes place, lands in a part of the Grassmann manifold. But that's what you want. So that's the idea of the proof. Yeah, in BH. You usually... No, that's associated. The fact that Z is minimal is one fact. And that fact is equivalent to another fact. That is exactly like I mentioned it. There exists a representation of the algebra into some Hilbert space such that, and this is associated to Z, such that in that Hilbert space there is a unit vector and Z has these properties, and that's a theorem, yeah, of course. And that's, no, it's not, it's associated to Z, yeah. Z gives you everything, the representation, the vector. It's not unique, of course, but that you have that. And because you have that, you can construct all these things, and then you can prove that the curve is minimal. So this is a theorem. And then I don't want to talk too much. So as I said before, this result shows that you have a kind of an exponential map. You can prove, therefore, that associated to any tangent vector, you have at least one minimal curve starting at the point with a given initial velocity. This fact alone does not allow you to prove, for example, that minimal curves starting at rho 0, all minimal curves starting at rho 0 will cover a neighborhood of rho 0. There's no way, at least I found no way, to apply any inverse function argument or something to prove that, and you cannot do that because of the structure of the minimal set. I mean, if the set of minimal z's were something more or less that you could treat, for example, flat or a subspace, or then I could perhaps do something with the inverse. But it's not near anything like that, so you cannot do that. And I don't know if these curves really cover a neighborhood of the point, even though you have not one, probably many curves starting at rho 0 with a given initial velocity. So that's strange. And well, in a subsequent paper that we wrote with the same irregulars that I wrote this, we tried to show this, to answer the second question, this question of about how, if you can cover any important set with minimal curves. And, for example, if there is a solution, this is a kind of solution to the Cauchy problem for geodesics. And if you can find a sort of a solution for the boundary value problem, right, for geodesics. And in that case, we could prove a theorem, but a much less satisfying theorem, because in order to be able to prove that given one point, all sufficiently close points to that point are such that there is a minimal curve joining both, we were only able to prove that in a restrictive case, namely the case where B, the sub-algebra, is what we called of compact type. Now, we call a sister algebra an algebra of compact type when the unitary group of this algebra is relatively compact in the strong operator topology. Now, strong operator topology is something I don't know if you know, and if you don't, really, it doesn't matter, because I really don't like this theorem. So, the strong operator topology is a topology of pointwise convergence of operators. That's clear, right? Pointwise convergence of operators. That's a strong, and it's very usually the unitary group is not compact in that topology. But in certain algebras, and in fact in quite a few algebras, that happens. If that happens, we were able to prove that the boundary value problem for close points is solvable, and also the Hopf-Rinow theorem for large geodesics is also solvable. So when the subalgebra is of compact type, then any 2 points in the homogeneous space can be joined by a curve that is minimal joining those points. So, well, that's what we could do in that case, but it's quite very unsatisfactory to me because, well, I really believe that if the algebra, subalgebra is a von Neumann subalgebra, this should be true, but I don't know how to prove that, so I am sorry. And then, since I was talking about infinite dimensional spaces, and I think many of you don't like them, and I don't like them either. So maybe I can tell you something in finite dimensions, which is maybe will attract your curiosity. In this business of finding minimal matrices, minimal operators, which in this case are minimal matrices, let me consider the case, following case. So consider A, the algebra of complex matrices n by n, and B, the diagonals, subalgebra of diagonals. And then, of course, I consider I would consider the self-adjoint matrices instead of the anti-self-adjoint, because it's the same by isometrically and everything by multiplying by square root of -1. So B, and I will consider A self-adjoint and B self-adjoint. And then in the process of applying the general criterion of minimality for operators to this particular case, one finds the following interesting fact. I think very interesting fact. So let A be a self-adjoint n by n matrix. And suppose if it's going to be minimal in norm, it better be, I don't know how to call that, the spectrum of A, it should be balanced with respect to 0, right? It should have a minimum eigenvalue opposed, the opposite of the maximum eigenvalue, because if not, you just translate it by adding a constant, and you get one of less norm. And since my sub-algebra contains the constants, of course, so let A be a self-adjoint matrix. I don't know. I would call it balanced. So the maximum eigenvalue is the opposite of the minimum eigenvalue. Be balanced. Then, an interesting phenomenon occurs if you translate the general condition of minimality to this case. And then, consider, let me call lambda the norm of A, and so minus lambda is also an eigenvalue, right? And let me call S lambda and S minus lambda the two eigenspaces corresponding to these two eigenvalues, and they are perpendicular, orthogonal. And of course, all the rest of the eigenvalues are between these two. And then this happens. Because I don't know how to use these things. Then this happens. So let me call n lambda the dimension of S lambda, and n minus lambda the dimension of S minus lambda. And I say, and then this happens. There are n lambda vectors, non-zero vectors, in S lambda, and I'll call them V1 up to V n lambda, and I will bore you writing this like this: V11, V1n, V n lambda 1, V n lambda n. So n lambda vectors in S lambda, and n minus lambda vectors in the other space. So they are W1. Wow. This is not the end of the world, right? Not yet. And that Wn minus lambda, which are written like this. Oh. Il faut pas. No, momentito. W n minus lambda 1. I'm sorry to write all this. Entonces, this happens that you have these n lambda vectors here and these n minus lambda vectors here, and the following equal weight thing happens, that there are these such that V1 squared plus V n lambda 1 squared is and so on for every in every coordinate. When Z is minimal and is balanced, these two spaces carry these two systems of vectors which have the same moment. This is a moment map of a certain Hamiltonian thing, and they carry this, and these things are equal in each place n. But reciprocally also, if you have two orthogonal spaces that carry such a structure, where you can find vectors in one and not orthogonal, orthonormal vectors in one and in the other, that add up, these absolute values add up to the same thing, then if you construct a self-adjoint matrix by putting on one of the spaces a number, a positive number, and the other of the spaces the opposite, and in the orthogonal of the sum of the two spaces, any operator, self-adjoint operator of norm less than lambda, this operator that you will get will have minimal norm. So I want to make propaganda of this geometrical object that I could call a kind of a, I don't know how to call it. It's a sort of a flag manifold of a special type. And it consists of pairs of orthogonal subspaces in C to the n of given dimensions, say, n lambda, n minus lambda, where you can find these. You see, to get such a space, you could just, if you find two vectors which are orthogonal and have the same moduli in each coordinate, you have an instance of this. And it's very interesting that's the simplest case. And it's very interesting to think how can two vectors in C to the n have that property, to be orthogonal and have the same moduli. And that depends on the possibility of constructing a certain polygonal in the complex plane of given lengths of the sides, because since the two vectors have to be orthogonal, you have the inner product to be 0. The inner product is a sum of n complex numbers. You put and this n, since they add up to 0, there is a polygon there that closes, and that the closing polygon means that there are certain inequalities that are satisfied, which are that one side is less than the sum of the others. And it's very interesting, and I don't know, this is a very, I think, a very interesting problem in itself, but it's also useful in the process of constructing minimal self-adjoint matrices, as I try to explain. Well, I think that's enough, because I want to see the football. Thank you.